All right, welcome to Physics Video 4.1. We're going to be learning about nonlinear motion this chapter, and we're going to start today by talking about what I call the circular motion basics. The objectives are listed on the screen here. You should, by the end of this video, be able to distinguish between the terms rotation and revolution. You should be able to understand the concepts of period and frequency and be able to find the period and frequency for a rotating or revolving object. And then finally, you should be able to understand the concept of what's called tangential velocity. Tangential is how you say that. And be able to calculate what the tangential velocity is for a revolving object. All right, so here we go. Like I said, this unit is going to be a unit on nonlinear motion. We're basically going to talk about two topics. The first topic is circular motion. We're going to talk about objects moving in, as the name would suggest, a circular path. And then the second topic will be projectiles, which is basically, you know, like if you throw a baseball across a field or something like that. Okay, so here we go. Newton's law has taught us that force causes an object's velocity to change. Okay, and so far, all of the examples that we've looked at have caused the object to change its speed. In other words, the object is either sped up or slowed down. But remember, there's three ways to change your velocity. You can speed up, slow down, or turn. And that's what we're going to focus on this chapter. So, as it says here, sometimes, however, a force causes an object to change its direction, which is another way to change the velocity. All right. So, if you picture something traveling in a circular path, you know, it's going around and around and around in a circle. As it does that, the direction is always changing, right? Sometimes it's going this way, sometimes it's going that way, sometimes it's going this way, right? The direction's always changing. And because of that, the velocity is changing. All right. So before we get too much further, we need to learn a couple definitions to better understand circular motion. So first of all, the difference between what's called rotating and revolving. So rotate. An object is rotating if it's spinning in place but not necessarily moving. All right. So unfortunately, I can't show you this because it's tough. But if you imagine, you know, a circular object like, say, a compact disc, that compact disc just spins around and around, but it doesn't physically move. So that is rotating. All right. In order for an object to revolve, it's got to physically move in a circular path. So if you imagine an object, maybe this is a car on a racetrack, that car is going to physically travel in a circular path. All right. So that's what it means to revolve. So if it rotates, it's just spinning in one spot. If it's revolving, it's going to physically move, 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 so that its location at one instant is different from its location at another instant. All right. So examples of each. An object that's rotating would be a compact disc or a record if you are more into the vinyl. A merry-go-round, either on a playground or at a amusement park, rotates, right, because it spins in place. Strangely, a revolving door, the door itself doesn't really move, does it? I mean, it turns, but it doesn't change location. So a revolving door is named badly because it just rotates. All right, and finally, the Earth every day rotates exactly one time. All right, now, objects that revolve. Like I said, a car on a circular track is going to be revolving. A kid on a merry-go-round, right? Check it out. Let's think about this. So here's a top view of a merry-go-round, right? The merry-go-round itself is rotating because it's just staying in place, right? Whereas if you've got a kid on the merry-go-round, hello, the kid is going to physically move. So the kid is revolving while the merry-go-round is rotating. All right, similarly, a person using a revolving door would revolve, and the Earth every year is going to revolve around the sun. It rotates once per day, that's why we have night and day, and it revolves around the sun, which is why we have, you know, that's how long the year is. Okay? So, two other super, super important definitions. These are colossally important. All right? So, the first term is what's called period. Capital letter T is the symbol for period. And the reason that capital T is the symbol for period is because period is a measure of time. Specifically, it measures the amount of time required for an object to complete one revolution or one rotation. So if I say to you, hey, that object has a period of 4 seconds, then what I'm telling you is that it takes the object 4 seconds to go around in a circle. Okay? Frequency, F is the symbol for frequency. It's got to be lowercase letter f, right? Because capital F is force. So lowercase f, frequency, represents the number of revolutions, or rotations, that an object completes per unit time. All right, a common example that some of you might be familiar with is on a record player. it has the frequency. You can set it at either 33 1/3 RPMs or 45 RPMs. This one, for whatever reason, I've chosen 60 RPMs, which isn't a real thing. But anyway, so if you had a record that spins at 60 RPMs, then I'm telling you that it spins 60 rotations per minute. I'm telling you the number of rotations that it completes per unit time. Okay? So period tells you how long it takes to go around once. Frequency tells you how often it goes around. It's telling you how frequently it goes around, how many times it goes around per unit time. If it helps you think of it, if I asked you how frequently do you brush your teeth, you might say 2 times per day or 3 times per day, right? So you're telling you how often it happens per unit time. In this case, 60 rotations per minute. Okay? So, at this point, I'm going to introduce you to Buzzy the Bee.
All right. Look, it's Buzzy the Bee. He is our circular motion mascot for the day. So what we're going to do here is we're going to take Buzzy the Bee and we're going to spin him around. I'm actually going to spin him around over my head. Hope you can see him there, yes. But before I do, I want to spin it this way so you can see the full circle. What I want you to be aware of here is that he's traveling in a circle, and the radius would be the distance from my hand, which is the center of the circle, out to the bee. If you think about it, that radius is actually just, whoops, the length of the string, right? Because that string represents the distance from my hand to the bee, right? So he's going to spin around like that, okay? And so we just finished here in the video talking about period and frequency. Okay, remember, period is a measure of how long it takes the bee to go around one time. So if I was to use a stopwatch and time how long it took the bee to go around, I would wait until the bee got here and stop it there. So it would be ready, set, start, stop. That time there between the amount of time it took me to say start and stop is the period. Okay, it's going to be a pretty small time interval, right? Now the frequency tells you how often the bee goes around. It's telling you that in a minute the bee goes around however many times. So I could look at the clock on the wall and start counting and count how many times he goes around in a minute. All right. The tough part is that in most physics problems, things don't move for a number of minutes; they move for a number of seconds. All right. And so our frequency is going to be, instead of so many revolutions per minute, it'll be so many revolutions per second. So it's going to be a much smaller number. What we're going to do here is we're going to actually time how long it takes for the bee to go around. Hang on, I got to remember what I did here in the video. We're going to time how long it takes him to go around 10 times. Okay. So I'm not actually going to do it, but what we would be doing is we would be using a stopwatch and timing how long it takes him to go. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that was probably about 8 seconds. I should have looked at a clock, but you get the point that I timed, using a stopwatch, how long it took him to go around 10 times. We're going to say that it was 8 seconds, and then use that to do some calculations. All right? So there you go. There's Buzzy the Bee. Whoa!
So hopefully I've edited in. We'll see if this works, me spinning the bee around. All right, so in that video you just saw, the bee was spinning around and around, and we could have, if we had wanted to, used a stopwatch and counted how many times he went around in some chunk of time. All right, so let's suppose that we'd done that, and let's suppose that we counted the bee and discovered that it took him, oh, I don't know, let's say he spun around maybe 10 times in 8 seconds. Okay, so we timed him in 8 seconds, he went around 10 times. All right, based on that, we can find his period. Remember, the period measures how long it takes him to go around once. So the idea is, if 8 seconds is the time it took him to go around 10 times, so 10 revolutions, that means when I divide that, I'm going to get 0.8 seconds per revolution. That would be his period. It's the time it took him to go around once, right? 0.8 seconds per revolution. Okay? So to find his frequency, now I want to know not how many seconds does he take per revolution. I want to know how many revolutions he gets per second. So I'm going to flip it over. The frequency is going to be the number of revolutions he completed per second. So that gives you 1.25 revolutions per second. Okay? Now, units, usually we just measure period in seconds. So I'm going to write this as 0.8 seconds. And it's understood that that's the time for one revolution or rotation or whatever. All right? And over here, the 1.25 revolutions per second, we usually just write as what are called hertz. A hertz is defined as a cycle per second. It's a repetition per second. Okay? So in this case, it's 1.25 revolutions per second. We abbreviate hertz Hz. Okay? So something that you should notice is that the period, to calculate the period, we took the amount of time that passed and divided it by the number of revolutions, right? We took 10 seconds. No, we didn't. We took 8 seconds and divided it by 10 revolutions. And to find the frequency, we flipped it over, right? We did 10 revolutions over 8 seconds, right? Please don't give fractions as your answers. You need to give me a decimal. Yeah. Okay. Now, this brings up an important, interesting side note, which is this. It turns out period and frequency are reciprocals, right? The period is 1 over your frequency. So in that example we just did, our frequency was 1.25, and our period was 0.8, right? Hertz in seconds. And it turns out if you do 1 over 1.25, it gives you 0.8. Or if you do 1 over 0.8, it gives you 1.25. So in other words, if you know one of these, you automatically know your other. If you know the frequency, you know the period, right? Okay, so something I should probably comment on too is this. Frequency measures how often it goes around per unit time, right? So a higher frequency just means it's spinning faster, right? It means it's going to go around more times per second, okay? So frequency kind of tells you how fast the object is spinning. Period tells you how long it takes to go around once. So the faster it's spinning, the smaller your period will be, right? In other words, the faster it's spinning, the higher your frequency is, the less time it takes to go around one, so the less your period is, all right? So they are inverses, okay? All right, the next thing we need to talk about is just some basics about circles. So at the right, we've got a circle here, right? So the radius is this, the distance from the center of the circle to the outside. The diameter is the distance all the way across the circle. And the circumference is the distance all the way around the circle, right? Please make sure you know these equations. I'll write them bigger in case you're watching this on an iPhone or something. The diameter is twice the radius. The circumference is 2 times pi times your radius, or just pi times your diameter. I would say that this is the one that's going to come up the most often, so please make sure you know that. All right? So the bee was spinning around and around and around in a circle, right? So it's probably worth our while to talk about how to find the velocity of the object. All right? Notice, though, because he's going in a circle, his velocity is always changing, right? Because his direction is always changing. So what we're finding here is really speed. We're finding the speed of the bee as he goes in a circle. In physics, we call that, and this is a fancy term for something very simple, we call it tangential velocity. All right? Again, tangential velocity basically just refers to the speed of the object moving in a circle. All right? So to keep it fairly simple, we're going to assume that the bee was moving at more or less a constant speed. So to find his velocity, his speed, we're just going to take the distance he traveled and divide it by the time it took. Specifically, we're going to use the distance traveled in 1 revolution and divide it by the time to travel 1 revolution. So here's your equation. Velocity is, whoa, all right, right there. Circumference over time, right? Man, all right, you get it. Velocity is circumference over time. Okay? We can do some simple algebra on that to come up with these equations. A lot of times I won't give you the circumference. A lot of times I'll give you the radius. So you can do 2 pi r divided by your period, right? So basically what's going on here is you can find velocity by either taking circumference and dividing it by time, or by taking 2 pi r and dividing it by time. Now, when I say time here, I'm talking about the time for 1 revolution. So please remember, that's the period. It's the time for 1 revolution. People mix this up a lot. All right? Now, it also turns out, using a little bit more algebra, instead of dividing by period, you can multiply by frequency. So you can find your velocity by doing circumference times frequency, or take 2 pi r and multiply by your frequency. This one is probably the one that I use the most often, for no real reason except that I tend to prefer multiplying over dividing because I don't like fractions. So there you go. So let's do a quick example. So let's suppose that Buzzy the bee, his circular path that he was spinning around on, which incidentally is the length of the string. Please make sure you understand that. All right, so let's say that his circular path had a radius of, I don't know, let's go with maybe 0.75 meters. Okay? So what we'd figured out was that he completed 10 revolutions in 8 seconds. So we knew that his period was 0.8 seconds. We knew that his frequency was 1.25 hertz. So to find his velocity, you can either do this, which would give you 2 times pi times 0.75 meters times 1.25 hertz. Or if you want, you can do this, which gives you 2 times pi times 0.75 meters over 0.8 seconds. And regardless of which one you do, you get the same answer, which is both of these give you 5.89 meters per second. So that means while the bee was spinning around, he was traveling approximately 5.89 meters around the circle every second. Okay? Please, please, please take the time to do both of these calculations and verify you get the same thing. And probably, similarly, take the time to do, where is it? This, and make sure that those work out, that you understand that your period and your frequency are inverses. Okay? I'm going to stop there, and have a good day.